So we're getting really close to being done with stress transformations. Might get through them today, probably not. Probably finish them on Friday. But I did post homework, okay, out on D2L. That's due a week from today, okay, Wednesday of next week, 5 p.m. I also put together the quiz that'll be up next week, okay, available Wednesday to Friday, just as we have been doing for some time now, right, the last 5 quizzes. So be ready for that, all right? The quiz and the homework obviously is all based off of stress transformations, right? So a lot of Moore's circle stuff, okay? And how that integrates into design. So today we're going to continue down our path. We're really just going to do a few more examples, okay? In the end, we've done a lot of examples, which I think is good because really the bulk of this material is all about drawing the circle, figuring out the center, figuring out the radius, and then from that, understanding that now we have essentially described any stress state in the material, any given orientation, okay? And that helps us as designers, as we know. And so one of the last concepts here that I wanted to talk to you about is this difference between what we would call the max in plane versus the maximum absolute shear stress, okay? And we talked on Monday about this concept of, in general, as engineers, we typically assume this plane stress condition, right? And a plane stress condition is that we really are only looking at one plane in our material because we're assuming that in the third dimension, right, our z dimension, our stresses are 0, okay? Our stresses are 0, right? Sigma z, tau xz, and tau yz, or tau zx and tau zy are all 0, right? So everything coming out of this, when we talk about this little lectern box, right? All the stresses acting on the front and back face of that are going to be 0, okay? And we really are only looking at, say, the x direction, right? The size of this box and the top of this box is the x and the y. And that would be our plane stress case. Right? So that's in plane. So that's the circle that we've been drawing, right? We have an x face and a y face. We have our coordinates that are established based on what is the stresses on those two faces. We plot them on a grid. We draw a circle around them. That's our Moore's circle. That gives us the stress at any orientation. Well, in reality, right, even though we're assuming plane stress, there is stress, right? It's just magnitude is 0, right? So on the front and back of that, there's a magnitude associated with the stresses on the front and back of that cube. And our stresses have a magnitude of 0. So what does that mean? Well, we have coordinates that we can plot on a Moore's circle, right? 0 is a point on our Moore's circle, right? It's the origin. And so we end up getting 3 circles, right? One circle is going to be attached to our XY plane. One circle is going to be attached to our YZ plane. And one circle is going to be attached to our XZ plane, right? So we have essentially 3 cuts we can make through this. We can cut it this way, that's our X and Y, right? We can cut it this way, which is our Z and Y, right? And then we can cut it horizontally, which is our X and Z, right? So we can get, for instance, right, if we started by just wanting to plot Moore's circle for our plane stress case, right, our X and Y, right, this guy here. So if we would just typically go through, we would find a stress element, right, at a known orientation. We would have magnitudes for each of those stresses on each of those faces. We would go through and we would plot them, right? So in this case, if we plotted, say 2 points, right, this might be our sigma x tau xy. This might be our sigma y tau yx, right? We know our shear stresses are equal and opposite on either side of our x-axis, right? Our x-axis is our normal stress. So we're going to be equal distance above and below, and then we're going to have some sort of magnitude for our sigma x and sigma y. So we draw this Moore's circle. So this red circle is what we've done in class, right? Okay. Well, at the same time, in the z plane, our stresses are all 0, right? And so we have this point, right here. All right, sigma z is 0, and we know tau xy or xz, tau yz also equals 0. So we have, if we started looking at the other 3 dimensions, right, the other slices of this box, we would have a point that sits right here, right? And so if we wanted to figure out, well, now in 3 dimensions, if we wanted any orientation of cutting it, right, we're going to cut this box this way to get our x and y. We're going to cut this box this way to get our z and y. And then we're going to cut it horizontally to get our x and z, right? Well, now we can rotate this cube in 3 dimensions, right? It starts getting very complicated. But it gets fairly simplified by just looking at these 3 circles, right? So now we would take our sigma x, right? So we get this plane stress case out here. All right, we have, that's our maximum normal stress or our principal stress 1, right? We know we've done that before. This is our sigma 2. That's our principal stress, right? Our minimum principal stress in the xy plane, right? And then we have this 0 point. Well, what do we call this 0 point? We call it sigma 3, right? The third principal stress, which ends up being 0 when we assume plane stress, because that's where we're assuming our coordinates are 0, right? Normal stress is 0, shear stress is 0, so we get this point. Okay, so we've been able to draw this circle. Once we've drawn this circle, we can get our principal stresses. Well, once we have our principal stresses, now we can establish the last 2 circles, right? One circle is going to be sigma 2, sigma 3. One circle is going to be sigma 1, sigma 3, right? So we draw these 2 circles. We got the orange one and the blue one. One circle is going to be associated with the, right, this will be our, say, the xz plane. This would be our yz plane, right? And that tells you now, if we took this block, right, and we were cutting it this way, and we've been looking at rotating it, say, in this direction, right? We're going to rotate it around this direction. Well, we can also rotate this cube this way, right? And we can also rotate this cube this way, around all 3 of its axes, right? We could rotate it about the x-axis, we could rotate it about the y-axis, and we could rotate it about the z-axis, right? And so that's what this is showing, is if we made those rotations about any one of those axes, these are the stresses you generate, right? And so what happens is, as you can see, the circles get larger in radius, right? And we know that the maximum shear stress is the maximum point, right, above and below our x-axis. So we end up with this point up here, right, and this point down here. And that point up there is what we would call our absolute maximum shear stress, because it is the absolute maximum stress in shear that we would see at any given plane orientation, right? Now we're considering it in 3 dimensions. We've considered the fact that we're going to assume that the stresses on the front and back of this cube, right, the z-axis are 0, but that has a magnitude 0. That has a point here on Moore's circle, and when we draw our 3 circles, which are attached to the xy plane, the xz plane, and the yz plane, right? The biggest circle we generate in this case is going to be this xz plane, and that xz plane circle has the biggest radius, which means that it has the biggest shear stress, and it's absolutely the biggest shear stress, right, out of all 3 planes, okay? If we were looking for the maximum in-plane shear stress, that's the magnitude we would be capturing, right? The xy plane. That's what all the Moore circles we've drawn to date are this xy plane. And if we grab the radius of that circle, well, that is the maximum shear stress if we were to rotate it in plane, right? questions? Yes.
Why is the XZ plane the largest?
It's just the largest right now because, well, I was going to show you that in a second, but because this sigma 1, right, we rotate it down, this x face would be the principal axis, right? So sigma 1 becomes this point. Sigma 3 is always the 0 point, and so we would consider this the xz plane. Right, the yz plane, and the, yes, Drew.
Are the circles always in?
No, so that's why I drew another one here, right?
Oh.
So I drew another one. And so what can happen is, oh, that's not right. I drew this wrong, sorry. This is beautiful, I can just do this. Well, I'm gonna make this consistent with colors here. Whoops. It's gonna be a very small circle. Come on. Quit it. Stop. Damn it. Won't let me move it. Okay. So if our initial Moore's circle, right, the xy plane we established, this red circle here, is all on the right-hand side of this axis, right, or all on the left-hand side of this vertical y-axis, right, then when we draw our three circles, we know the point that we're missing is always going to be the 0, 0 point, right? And so our large circle, right, is going to not be in plane, right? Because we're going to make a larger circle because our point, whether this circle's on the far right or the far left, we're going to make a bigger circle than our in-plane circle, right? But what happens is what if our initial element, right, has our 2 points we plot, right? We're going to plot 2 points. This might be sigma x, tau xy. And this down here might be sigma y, tau yx, right? And we draw a Moore's circle, and that Moore's circle now extends on the other side of our vertical axes, right? Well, that third point, sigma 3, is always going to be sitting in plane stress is always going to be sitting at the origin, right? It's zeros. You know this point. And so when we start drawing circles between sigma 1 and sigma 3 and sigma 2 and sigma 3, right, these circles are going to be smaller than our in-plane circle. So sometimes it works out, right? Tau max in plane is the same as tau max absolute. And all that has to do with how does this red circle land, right? The in-plane circle, right? And if it lands to where the origin or the center of our diagram is within our in-plane circle, then the remaining two circles are going to be inside it, right? Whereas if our circle is all the way on one side or all the way on the other side of the origin, then we're going to create this larger circle, and our in-plane maximum shear stress is not going to be equal to that absolute. Does that answer your question, Jim? Kind of, sort of?
Yeah.
Still confused. How are you confused? Ask a question.
How do we figure out which circle's which, I guess?
Well, you will always be drawing the in-plane circle first, right? How we've done it in all the examples. So you draw the red circle, right? And from knowing the red circle, you're going to know sigma 1 and sigma 2, right? Those are our principal stresses. We can know those points. We've done that in the examples already. We're going to figure out our 2 points. We're going to figure out a radius. We're going to know where the center is. We're going to, from that radius and center, we know what sigma 1 is and sigma 2 is, right? Well, we know, we always assume plane stress, okay, in this class. So we know that sigma 3 is always 0. So we can draw another point here at 0. So once we know sigma 1, sigma 2, and sigma 3, right, we can just draw circles between those 3 points, right? Between sigma 3, sigma 2, sigma 2, sigma 1, we've already done, and then sigma 1 and sigma 3. And we do that based on wherever this in-plane Morse circle that we draw is at, right? The XY plane. And then we'll get these 3 circles. And you just want to grab the largest magnitude of the circle, of the largest circle. Yes?
If your origin always cuts through your in-plane circle, will that mean that your 2 inner circles will always have to go through the origin and that's...
Yes, so that's what I was trying to depict between these two, right? You kind of have 2 options when you draw your Morse circle, right? Your Morse circle could be like in the XY plane, right? I'm going to give you a stress element. It's going to be a little cube, a block. Okay, it's going to have stresses on the 2 sides of it, right? Just as we show up here, okay? So you're going to be able to plot this red circle. If this red circle is all on one side of the y-axis, right? If it's all over here, or if it's all over here, you're going to get this behavior, right? You're going to make a circle, ultimately, that's larger than your Morse circle you generated first off. That's if your in-plane circle is on completely on one side or the other of the y-axis, right? Does everyone kind of see that? And the other option you have is if you draw this red circle, right? We're going to give you a stress block. It's going to have stresses on the x and y face, and you plot those, and this happens, right? Where now your y-axis comes in contact with your circle, right? Where you have parts of the circle on either side. Well, if you have parts of the circle on either side, then when you draw your 3 circles, it's going to look just like this, right? And what does that mean? Well, that means the largest circle you're going to draw is going to be the one that you draw first, right? And all that means is that the maximum in-plane shear stress in your material is the maximum absolute shear stress in the material, right? Can't get any bigger than the stress that you see when we look at just the XY plane. Okay. Does that help? Sweet. Any other questions? Kind of a tricky little concept, but it's worth noting. Yes?
What if like your first circle goes through the origin? Like the first one that we drew in our notes?
Then sigma 2 would be sigma 3, and that circle would have 0 radius, right?
Okay, so you just have to...
Like you're saying that this red circle slid over here to where we drew it and sigma 2 was at 0.
Yeah.
Yep, then that would mean that sigma 2 is 0 and sigma 3 is 0, and the circle, this blue circle, would now have a radius of 0, right?
So then there's only one circle.
Then there's only one circle. Yep. And again, you'd have this case, right, where your maximum in plane is the maximum absolute. No, that's a good option. Anything else? Okay. So we're going to use this concept moving forward when they ask us for what's the maximum absolute shear stress, right? Which is important to us, right? Because if we have this case going on, then sweet. You know, if we capture the maximum in plane, if we were to draw this one red circle and not consider the orange and blue circles, when we figure out our maximum shear stress, we relate that to the materials, it's all fine and dandy, right? We've captured the maximum absolute shear stress. Well, problems can arise when we don't capture the maximum absolute shear stress, and there's an orientation in this material in 3 dimensions. You take this block, right? And now instead of just rotating it this way, the XY plane, we're starting to rotate it in 3 dimensions, right? We're going to start doing all of this. So there's an orientation in there where we have a greater shear stress. And that can be bad, right? We might say it's okay because all we do is grab this. Well, in reality, somewhere in that material, at some orientation, there's a stress that's greater than that. And that could be greater than the stress the material can handle, right? Okay. Maximum in plane versus absolute. All right. So with that in mind, we're going to go through another example. This one takes a little while. So we've got a point in a structural member is subjected to plane stress. And what does that mean? Well, we know that our normal stress on the Z face, right, the front and back of that cube is 0, and our shear stresses acting on those in those directions are also 0. And they tell us what those stresses are, right? So we've got this stress element, it's oriented as shown. We've got our two stresses on each of our faces, our shear stress and our normal stress. They want us to draw a Mohr circle for the stress state. They want us to determine the principal stresses, the maximum in-plane shear stress acting at the point, and illustrate that on an element rotated at the angle, okay, of the principal stresses. And then they want us to determine the normal and shear stresses on the indicated plane, show these on a sketch. Indicated plane, right? So they're showing us that we're going to cut this element at a 4, 5, right, triangle. And then finally, they want to determine the absolute maximum shear stress at the point, right? So we've already, up above, they asked us for the maximum in-plane shear stress. Well, now they want us the maximum absolute shear stress. Okay.
Is this basically like everything we've done so far in one problem?
Everything we've done so far in one problem, correct? Okay. So what do we got to do first? Well, we got to draw a Mohr circle. I made it real easy for you guys. Boom, we drew Mohr circle. Okay, should be 3 pages ahead, okay? You're welcome, all right? Don't say I never gave you anything. You have this, right? In your notes. Easy enough? Okay, sweet. All right, this is nice and beautiful. Probably better than any of the circles you've drawn to date, okay? So we got this beautiful Mohr circle, right? Well, what the hell does this mean? There's all sorts of lines on this, right? Well, this incorporates a lot of other things that we're doing, okay, as we move through this problem. But in reality, which one of these circles would we have drawn? The outside circle, the inside circle on the left or the right? Which one would we draw first? The outside, right? Because we have our 2 points, known points. We have this X point here and a Y point there. Well, if we look at our stress block, okay, we got our stress block here. We've got our coordinates, X and Y, right? Those coordinates allow us to establish our X face and our Y face. The stresses on those faces are our coordinates. We would then plot those coordinates, right? Go back, forward here, okay? We're going to plot those coordinates. We've got negative 3.8. This we know is positive shear stress clockwise, right? If we twisted our hand, right hand rule, it'd go counterclockwise. Okay, thumbs pointing out of the page. This is positive. This is negative shear stress. What does that mean? Well, if we look on the X face, right, we've got coordinates of normal stress and shear stress, right? Well, our normal stress is compressive. What does that mean? When we go to plot a Mohr circle. It's negative, right? It's on the left-hand side down here, just as they show. Also with the shear stress, right? We know the convention for shear stress. If it's on the positive face acting in the positive direction, it's a positive shear stress, right? Or we could use the right-hand rule, and if we looked at this shear stress, these stresses on the X faces, right? It's trying to rotate our block counterclockwise. Okay, so it's on the positive face, positive direction. It's a positive shear stress. We're going to plot it down on the bottom end of our Mohr circle. Or we could look at the shear stress directions, and if it's trying to rotate our block counterclockwise, then we're down here. So what does that mean? Well, that's our point here, right? Negative 3.8, comma, 5.7. Similarly, if we look up here, well, now we've got 9.4. It's going to be positive. And then it's our... I drew the same arrow going the same direction. That does not make sense. Buttons always fuck this up. Whoops. Trying to add a picture. There we go. It's actually clockwise up there, right? So if we look at the Y face, that 5.7 is trying to turn that block clockwise. So we're going to be up there, 9.4 and 5.7. That's our coordinates. We plot our 2 points. Okay. Yeehaw. Keep going, right? Now we got our 2 points. We draw a line between them. we're going to establish a center, right? The center is wherever it crosses the x-axis. We're going to have some sort of radius. I'm going to change this to red so we can start seeing it. So we have a center and a radius. Our radius is going to have, we're going to establish the radius based on our x and y legs of our triangle, right? So if we go back up to the beginning here, once we've established our 2 points, we draw a line between them. We can then establish our center and our radius. If we start by looking at, so this is part A, we're going to establish our radius. We know our radius is this equation, which is essentially just establishing what's our x contribution, yx squared. We get 8.72 KSI, right? All I'm establishing there is Pythagorean theorem, right? Getting the 2 legs of that triangle, squaring them, summing them, and taking the square root. Figure out the hypotenuse. That's our radius of our circle. Center, well, that's our average stress. It's going to be sigma x plus sigma y over 2. Negative 3.8 plus 9.4 all over 2. Our center equals 2.8 KSI. And so 2.8 KSI. So now we have our points, right? We have our center, we know is 2.8. Our center's always on our x-axis, so our other coordinate is going to be 0. And the radius we now know is 8.72 KSI. So we know our radius, we know our center, we scribe our circle, and that's the answer to part 1, right? They ask for a Moore's circle associated with the stresses on the element given, right there. And we get that. And this gives us every stress that this element would experience, right? If we were to take this element and start rotating, right? As we start rotating it, now we're starting to look at stresses at different planes, right? At different planes, and those stresses are going to change. Any questions there? Done that quite a few times now. Okay. No questions?
Is the center part of the answer too?
We always want to try and establish that center point, right? Because that center point is then going to allow us to calculate any stress anywhere else, right? So I would consider it part of the solution for Moore's circle. Okay. The next part is, right, determine the principal stresses and the maximum in-plane shear stress acting at the point. And they want us to illustrate an element with rotation angle at the principal stresses. Right? Well, if we looked at this, right, what are our principal stresses? If you were going to use an equation, how would you calculate sigma 1 and sigma 2?
2.8 plus the radius?
2.8 plus the radius, and then 2.8 minus the radius, right? So it's the center plus the radius, and center minus the radius. That's all we need to do, calculate that. We're going to go back up. Excuse me. Right, part B. They want us to figure out the principal stresses. Well, we know sigma 1 or sigma P1, or the first principal stress, is our maximum in-plane stress. So sigma max. And that is the center plus the radius, right? We got that just from the circle. And as Drew mentioned, 2.8 KSI plus radius 8.72 KSI, we get sigma 1 equal to 11.52 KSI. Sigma P2, sigma min, center minus the radius, 2.8 minus 8.72, we get sigma 2 equal to negative 5.92 KSI. Right? If you're running these calculations, say in the homework or on a quiz, look at these and then look at your Morse circle, right? This should be, I mean, when you draw your Morse circle, should be relatively to scale. Okay? Looking at this, right? This was 11 and this was 5. Makes kind of sense, right? Kind of halfway on the left-hand side as we are on the right-hand side. Sigma 2 we got was negative, right? Make sure you validate what you're getting. It's easy to just make a fat finger error and take the wrong number or use the wrong operator or something like that, right? Don't just blaze ahead. So we've got our two principal stresses. Well, what's our maximum in-plane shear stress? Not a trick question. 8.72, right? It's the radius. It's always the radius is our maximum in-plane shear stress. It's the radius of our in-plane circle, right? The circle we drew, the outside circle. So this is the, radius. So tau max in plane equals the radius 8.72 KSI. Next, they asked us to illustrate on a stress block the principal stresses. If we were going to illustrate on a stress block the principal stresses, right, what's one more thing we need to know off a Morse circle to do that? The angle, right? How far we need to rotate our current stress element state, right, the one that they gave us, to our new stress state, which are our principal stresses, okay, in order to depict that. Well, the angle we want is this angle right here, right? We want to know how far do we need to rotate downward in order to get to that principal stress. So we need to know this angle right here. We call that angle alpha, right? And if we call that angle alpha, in order to get that angle, we know we can use trigonometry, right? The inverse tangent, which would be the inverse tangent of the opposite over the adjacent of this little triangle we made in light green, right? Where our y is our opposite and our x is our adjacent. Well, if we look at this, right, our adjacent, our x, is really just the x coordinate, right? Opposite, oh no. Our opposite, right, our y, sorry, our y coordinate, right here, is really just the y coordinate of our y point, right, 5.7. Our x coordinate, okay, is going to be the x coordinate of that y point minus the center. Right? Does that make sense to get us our x or adjacent? So we can just use that. Now we're going to figure out, okay, our alpha, I'm going to call this alpha p, or the orientation for our principal stresses. We're going to say that that equals the inverse tangent now of the opposite over the adjacent, or the inverse tangent if we plug things in, right? We said that the opposite was just the y coordinate of our y point, and then our x or our adjacent is the x coordinate of our y point minus the center, right? 2.8. We get a sigma p equal to 40.8 degrees.
The opposite was 9.4.
What's that?
The opposite was 9.4.
No, the opposite is, what? Yeah, opposite is our y coordinate, right?
Oh,
Our y coordinate. Opposite of this angle, adjacent to this angle. So the opposite would be the y coordinate for y, right? That would give us this. And then our x coordinate, or our adjacent, is going to be the x coordinate, 9.4. Well, 9.4 is 2.8 from the center, right? So we need to take that 9.4, which is the total distance, minus this center distance to get us the green distance. Okay, we got 40.8 degrees. Is that it? Is that our orientation? No? What is our orientation? Half of that, right? So we would take 40.8 divided by 2. Theta, alpha p over 2, right? Or 20.4 degrees. Right? And that 20.4 degrees is clockwise, right? We have our 2 points. We rotated clockwise. Well, that means we would take our element. So we have our original element. Looks something like that, right? We have stresses attached to it. Right? It's essentially the stress block up in the right-hand corner. I just duplicated it down there. That's our known stress element. What's up, James? Come on in. You could use some of this.
No, it's okay.
So we have our original stress element, right? Now we figured out what's the angle over which we need to rotate this element to get our principal stresses, okay? And we know those principal stresses now. Well, we know that it's 20.4 degrees, so if we establish, right, this is our x-axis, this is our y-axis, we know we need to rotate downward 20.4 degrees, right? We need to rotate these axes down clockwise 20.4 degrees. So we're going to establish a new, start at the center. We're going to do something like this. Right? Nice, beautiful straight line. It's coming off at the center of our element at 20.4 degrees, right? We're going to rotate it. Our new element is going to be oriented on this somewhat, sort of, square enough, okay? Our coordinates now, right? We have x and y coordinates still for this element. They're just rotated downward. So we have our two principal stresses, right? Our maximum is 11.52 KSI. Sigma 2 is negative 5.92 KSI. Okay. Now we have our stress block. We rotated it downward, right? We're going to have stresses on either side of this block, right? If we start on the x face, which value should we attach to the x face? Is it sigma 1 or is it sigma 2? Sigma 2, right? And that's because if we look at our stress block, or our Morse circle, right? We rotated downward. This was our x face, that was our y face. So when we rotate up, right, our x face now becomes sigma 2, our y face now becomes sigma 1, right? So we can just, based on the Morse circle, we've established what the directions, wrong way. We've established the direction. So now if this is sigma 2 on the x face, we're going to get a compressive stress, sigma 1 on the y face, which is 11.52 KSI. This is 5.92 KSI. And that is our principal stresses, okay, illustrated at an orientation, right, that matches the required orientation of a stress element in order to capture our principal stresses. Okay? So if this was a structural material, okay, and we had a stress element, somehow we figured out these stresses, right? Based on the combined loading, whether it was pressure, axial load, torsion, bending, all of those things combined, right? We could establish the stresses in this structural element, okay? Look like this. Well, if we were to cut this structural element at 20.4 degrees, okay? The stresses on that plane, for instance, right? If we cut it at 20.4 degrees, right? We sliced it perpendicular to that face, we would be trying to pull that structural material apart, right, with 11.52 KSI. That's the stress we'd have along that plane. If we cut that thing at 90 degrees to that, right, a plane that's oriented with our X face, well, at that orientation, now the material is actually trying to compress itself. It's trying to come together, okay? Right. A great depiction of this is like, if you, I don't know if anyone else, I was trying to bring in chalk, but it's actually hard to find chalk these days, okay? If you took sidewalk chalk or even like your white chalk, okay? And you took a piece of chalk and you twisted it in your hands, all right? The failure over which that chalk would break, it actually breaks in a spiral. It's really cool, okay? Because we're putting it into torsion, and we know torsion puts shear stresses on it, right? So we're actually trying to shear off that stick of chalk. Well, when you depict that known stress state in that chalk, where the hell are we at here? Okay. And we put it into pure shear, right? It has zero normal stress. It just has shear stress, right? The 2 points we're going to plot are going to be along this y-axis. So what does that mean? Well, if we rotate Moore's circle and figure out our principal stresses, okay, that's going to be 90 degrees. Well, in the real world, that's 45. So if you took a piece of chalk in your hand and you just twist it, it's going to fail in a spiral, and that spiral is going to be at a 45-degree angle. Because when you twist it, that 45-degree angle, you're going to have a big compressive stress in one direction, and then in the other direction, you're going to have a big tensile stress. Right? It's actually going to be wanting to pull the chalk apart. I'm going to bring in some chalk because I feel like you guys don't believe me. Okay? I'm going to bring in some chalk. You can just put it in your hand and twist it, and you'll see it'll fail in a spiral. It's fucking cool. Okay? All right? It is really cool. And it goes to show you that depending on the material, right, chalk is very brittle. It's not very good in tension, okay? It can handle the shear stresses, obviously, but it can't handle the fact that you're trying to actually pull it apart. It has tension in it. It just, the tension that's in it is at a different orientation, and you're not even applying a tension force on it, right? If you were to pull the chalk apart, right, put a tension force on it, you know it's going to break in half, right, perpendicular. But when you put a shear stress on it, okay, it finds the plane that has a big tension stress in it, right? And that plane depends on the initial stress state. And if we put it in pure torsion, okay, we're going to have these two dots on our y-axis. Okay, our principal stresses are going to be 45 degrees to that, and you're going to get this 45-degree spiral, which is really cool. Okay, Google it too. Yes.
Why is sigma 1 like on the y-axis now and the block that you drew that was 20 degrees?
Why is-
the last thing that you drew?
This thing?
Yeah.
And your question is, why is this?
Yeah, like how do you know that 11.52 is like on the y and then like 5.2 something?
Okay, the reason why you know that is because when you follow your rotation on Moore's circle, right? When we establish Moore's circle, just like this, the 2 points we plotted were the x face and the y face, right? And then we figured out this rotation angle and said, okay, we've got to take our 2 points that we know, that stress element that's up there, and we need to rotate it clockwise, right? We're going to take that point, we're going to rotate it down the circle until it hits YP1. Then we're going to take this point, we're going to rotate it upward until it hits YP2. And these 2 points are attached to the sides of our element,
Oh, I see.
right? So we've got our X and our Y sides. So Y face, when we rotate it, it's going to be sigma P1. So that's why when we rotate it, that sigma 1, right, is now sigma y. Sigma 2 is sigma x, right? Those are just going to be the stresses that are acting on that face. Okay. Okay. All right. Any other questions? Okay. So we're going to jump to part C. Part C asks us, determine the normal and shear stresses on the indicated plane and show these stresses on a sketch. Well, we have these, they told us, right? They said, okay, we want to, maybe they decided they're going to connect this material at this given angle, okay? Or they're going to change materials or something, right? Something's important about this orientation in our material. And they want to know what's going on this face, right? So we've got the dimensions of a triangle on that face. And we can figure out what is the stresses on that face, right? So if we look at what we were doing just a second ago, let's go back here, okay? And we attach, this is our X face, this is our Y face, right? So we attach, we have coordinates on this element. And now we're going to rotate this element, and we want to know what's going on in this face. So we really need to look at, okay, what's going on this X face, and if we were to rotate it to orient to the face of interest, what are our stresses? So we really want to know what's that theta, right? Because we're going to take the X face that's vertical, and we're going to lean it back till it's oriented with respect to this face, right? And in order to do that, well, now we've got this triangle. We know the opposite and the adjacent. They gave us 4 and they gave us 5. So I can say, right, for part C, theta equals the inverse tangent of the opposite over the adjacent, or 38.66 degrees. Right? So again, what are we trying to do? We're trying to take the original stress element and we're going to rotate it counterclockwise, right, to the left now. We're going to take that X face, we're going to pull it back 38.66 degrees. So if we drew what this would look like, we're going to take our stress element, right, sitting there on the right-hand side, and we're going to lean it back to 38.66 degrees. And we want to know what's going on our X face and our Y face, right? Those faces are still there. We've got this X, Y coordinate. We just rotated counterclockwise a little bit. And we want to figure out what's going on there. Well, that's where we use Moore's circle, right? And we're going to stop. Just never get enough. There's never enough time. Okay? You start talking about chalk.